So we have this theorem. So we have this theorem. This is what we want to show. Okay, this theorem. Okay, suppose that A star is a group. And then we have B is a subset of A, and B is a finite set. Then B star is also a group. If and only if star is closed on B. Is that okay? So we just need to check whether star is closed on B. That's it. We don't need to check the other 4 cases. So the proof So first of all, this direction. If we know that B star is a group, then star must be a closed operation on B, right? That definition of a group. Okay, so this is by definition. So nothing special. By definition. So we don't need to prove anything. Okay, now how about the other side, backward? Okay, so suppose that star is closed. On B, okay. Then, for every B1, B2, B3, we must have B1 star B2 star B3 is equal to B1 star B2 star B3. Since B is a subset of A and star is associative. On items of A. Is that okay? So we just need to check close. Okay, close, and then it implies that B1 star, B2 star, B3, this thing, and B1 star, and then the product, the result of B2 star, B3 is well defined. It is still in B, and they have to be the same. It is because they are all items from A originally. A is associative. Star is associative on A, so that means that these two has to be equal. Is that okay? Okay, good. And now, what is next? Okay, so we still need to show that the identity exists. So how we can show? Okay. Next, okay. So the proof continues here. Say next, consider a certain item. Consider an element B in B. Okay, so we get B. So we start from B, and then we get B star B. Okay, and then we get B star associative. I don't need the bracket. Star B, and so on and so forth. Okay, so I get a shorthand notation. This is like B times B, right? So I call it B squared. Is that okay? Okay. Although this could be a plus operator. I call it b squared. 2 times of itself on the same operation. So this is b cubed. Okay, so I have a lot of things. Okay, so eventually, I have a lot of items, but eventually, 2 of the items must correspond to the same item in B. So I get B. So let's take a look of a finite. So for instance, we have a finite. So let's say we have this one, 0 degree, 30 degree, 60 degree, fewer. Okay, let's try this one. Let's try this one. Let's try 0, 1, 2, 3, 4, 5. And then the operator is mod 6. Is that okay? This is a group, right? This is a group. Okay. So let's consider this one, 0, 3. More. Let's try 0, 2, 4. More 6. This is a subgroup. Okay. So what we are going to do, we take an element, apply it again and again. So 2 plus 2, you get 4, and then plus 2, you get 0, and so on and so forth. At a certain point of time, you must have 2 items. They are the same. Reason. What is the reason? Reason. B is this set is finite. We need this set to be finite. So we cannot keep on getting a new item again and again because we'll run out of items unvisited, right? Pigeonhole principle, it is like, so if you look at B squared, B cubed, B4, B5, and so on and so forth, and let's say the size of B is like 10. If you have 11 items there, then 2 of them must be equal. Is that okay? So we must have, so eventually we will get some B to the power I, and then B to the power J to be the same. Is that okay? Is that okay? Then let's say J is larger. J is larger than I. Then this implies what? This implies B to the power J minus I is an identity element. It is because B to the power J minus I times B to the power I is equal to B to the power J. And then it is equal to B to the power I. Is that okay? Because we have, because B to the power I multiplied with B to the power J minus I is equal to Bj, and then it is equal to Bi itself. Is that okay? So there is some item that multiplies with B to the power I, you get back to B to the power I. Is that okay? Okay? And then this item is in A, and then in A there is only one item that has this property. So in that sense, it implies that the identity element is this one. This is the identity element as well, not just in B, but also in A. Is that okay? And then this identity element is obtained by doing operations on B only. Because we have assumed that B, the star operator, is closed. So you can have B, B squared, B cubed, B4. All these items must be in big B. Big B and star is closed on big B. So you can start from small b, you get B squared, B cubed. All these items, B4, B5, B6, all the items must be in the big B. So in particular, the identity is also in the big B. Is that okay? So we just start from the closed thing, the closed assumption, and then we have also checked that identity is also appears in B. Okay? So we are getting more closer and closer to show that this is a group. Okay? Is that okay? So what is remaining? Okay, so what is remaining? It remains that every item of B, you can find an inverse in the set. Is that okay? Okay? So that's not difficult. Okay? So there are two cases. So case 1, if B is the identity, so the inverse is itself, and then it is in big B. Is that okay? Now on the other hand, B is not the inverse. If B itself is not the same as the inverse E, then what? And then B to then what? Then to get back to the same. Okay, so from B square and so on and so forth. So let me see. So then it implies what? Then it implies this implies let me see. Okay, or I use a different way that is easier to check. Okay, so look at this. Okay, let's take a look of this one. So here we have just discovered that b to the power j minus 1, j minus I is the identity. So let's take a look of the value of j minus I. If the value of j minus I is greater than 1 or greater than or equal to 2, then b to the power j minus I minus 1 is the inverse of b. Is that okay? On the other hand, if j minus I, if it is not greater than or equal to 2, but then j is greater than I, then it means that j minus I is equal to 1. Is equal to 1. Then b to the power 1 is the identity. This means that this is the identity. So we will have b inverse is equal to b. Okay? Is that okay? So in all the cases, no matter what happens, so no matter which elements b that you start picking, you apply the operator again and again on itself until you get the identity. So you get b to the power j minus I will become the identity. So in that sense, we can also find out what is the corresponding inverse of b. Okay? So it depends on how many steps you take. So if b, you take one more step, you get to the identity, then this must mean that this is the identity. Is that okay? And then, so the, not that, yeah, bj minus I, right? Let me see. So it depends on this one, bj minus I. Okay, so it depends how much step you do operations. If you do nothing, you get b to the power 1, which is already the identity, then b inverse is equal to b. But if you get 2 steps, then b inverse is just b. If you get 3 steps, then b inverse is b squared, and so on and so forth. Is that okay? So no matter what happens, then the inverse of b for any item in the big B is well defined. It is in the set. So in that case, we have shown that if star is a closed operator on B, B star satisfies all the properties of a group. So B star will be a group. Is that okay? Okay, too long thing. Okay. So, but there are some tricky things here. So we need B star to be okay. This is a tricky point. We need B to be finite for this proof to work. Where does we rely on this fact? Which part of the proof we need B to be finite? That part, the identity. Is that okay? The identity. Okay. So if a set may be infinite, like E plus is infinite, right? You start from any item, let's say 3. No, 3 is not even. You start from any item, let's say 2. 2 is an even. You add 2, you get 4. You add 2, you get 6. You add 2, you get 8. There's no way that you can get back to the value 0, which is the identity. Okay, so finite is needed for the proof to work. Okay, but if the set is finite, then it is much easy. You just check close, because checking associative is very tedious. You don't want to check associative, and then just checking it is close, then it is okay. Okay. So in a sense, okay, for this example, let's say we know that this is already a group. And to verify whether this is a group, we just need to check whether this operator is closed. You don't need to check associative. You don't need to check inverse. You don't need to check identity. Is that okay? Okay, let's take a 10-minute break, and then we will talk about. So here we have done subgroup. Okay, let's take a 10-minute break, and then we will continue the discussion on coset and the Lagrange theorem. Okay.